Go's concurrency model and scheduler are super confusing, and most articles and videos you'll find on them explain them in very abstract terms without telling you exactly what the runtime is doing to manage Go routines. So I wanted to make a video that goes into a bit more detail. I went down a bit of a rabbit hole on this one, but the whole process really helped me with understanding how concurrency works in Go. And I'm hoping that watching this video will give you that same understanding. I'll slowly build up to some more complex flow diagrams, but to start, I wanted to give a quick overview of how Go routines work on an actual machine. Okay, so let's say we have a Go routine. It's being executed on an OS thread, and that OS thread is running on a CPU core. This is the normal, boring state of a Go routine while it's executing. The interesting part comes when you want to swap from executing this Go routine to a different one. So let's say this Go routine completes and we want to execute a new one. The Go runtime will check a bunch of different queues for a Go routine that's runnable, and then it will execute that on the same OS thread that this Go routine was executing on. The key point here is that the OS thread is being reused. If you had to spin up a new thread for every Go routine you started, it would slow everything down. So the Go runtime swaps the Go routines manually on top of the computer's own scheduling layer. But in order for the runtime to do all this, we need some way to track these individual pieces. And this is where the GMP model comes in. If you've done any reading into Go's concurrency model before, you've probably come across the GMP model. And most articles explain things correctly, but they tend to be too abstract to really deeply understand what each of the pieces is. So let's go over this. First, G, M, and P are all just structs. The runtime holds instances of each of these struct types and uses them to coordinate what Go routines are run where. Each Go routine is represented by an instance of the G struct, and then each OS thread is represented by an instance of the M struct. But this is where it gets confusing. Officially, P stands for processor. So you would think that each instance of a P struct would represent a single core on the machine. But that is wrong and very confusing. The P struct instances do not represent CPU cores. What P does represent is the right for an OS thread, represented by M, to run a Go routine, represented by G. You can think of it kind of like a car key. If I have an M instance and that M instance has a Go routine that it wants to run, it needs the key to actually start that OS thread up and start running your Go routine. So in the runtime, a G struct and M struct pair is only allowed to actually execute the Go routine if it has an attached instance of a P struct. So then, why do people relate the P struct to processors on the machine? When the Go runtime starts up, it will allocate a specific number of P instances. And that number is equal to the Go max procs environment variable, which defaults to the number of logical processors on the machine that Go is running on. So if we have 5 cores, Go max procs will default to 5, and then 5 P struct instances will be created when the runtime starts up. And again, each of those P instances acts like a key that lets you run a single Go routine on a single thread. So the true purpose of the P struct is to act like a pseudo lock that limits the number of threads that can be executing on the machine at once. And logically, if we want the least contention between OS threads, then the number of P struct instances should be equal to the number of processors. But you can manually set Go max procs to be greater than the number of processors, which means you would be trying to run X number of OS threads on less than X number of cores. So you end up getting an oversubscription problem where you're relying on the OS itself to split time between a bunch of different OS threads instead of just relying on Go's own scheduling that uses Go routines on top of a limited number of threads. And oversubscribing like that will generally lead to worse performance for the CPU overall. So, to summarize all that, G is a struct, and each instance of the struct represents a single Go routine in your program. M is a struct where the instances represent an OS thread, and P acts like the key required to run a Go routine on a thread. So the number of P instances limits the number of parallel threads that can be running. And if you're still confused, that's okay. I was too. Just keep watching. Learning all the details behind this definitely clears it up a lot. So let's take a look at the actual internals inside these structs. First, the G struct representing a Go routine. I will note that this is nowhere close to all the properties that are in the struct, but I narrowed them down to just the ones you need to more or less understand what's going on. The first property here is Schedule, and it's used to save Goroutine context when you switch between the Goroutines that are executing on a single thread. So if I'm running a Goroutine and I want to switch to a new one, first I need to save the currently running Goroutine state in this property. And then when I switch back to that Goroutine, I can retrieve that state and start executing from where it left off. Next up is the stack property, which holds the address range for the stack of this Goroutine. Each Goroutine you spin up is allocated a small stack to start with. And so this property has the lower and upper bounds of that stack in memory. Next up is M, and this is a pointer to an M struct, which again represents an OS thread. So populating this field is how the runtime associates a Go routine with an OS thread. And then last is the atomic status property. There's a huge list of all the statuses in the actual source code, which I'll leave a link to in the description. But the most important ones are runnable, when a Go routine is ready to be run on a thread; running, which means a Go routine is currently executing; syscall, which means the Go routine is blocked by a OS thread blocking system call; waiting, which means that the Go routine is blocked by a Go mechanism like channels or a wait group; and dead, which happens when a Go routine completes and lets the runtime reuse the already allocated structs for any other Go routines you might spin up afterwards. Next up is the M struct. The first property is curg, which is a pointer to the Go routine that this M is attached to. So the relationship is bidirectional. The next is G0, which is a pointer to a special system Go routine that's used to run scheduling code and other runtime code. When an M is allocated, the G0 system Go routine is also allocated. And you'll see how this comes into play when I go over how Go routines are swapped out. And the last property is a pointer to a pstruct instance. And again, each pstruct instance acts like a key that lets the M and G pair execute the Go routine on a thread. So setting the P property is how you attach a P instance to an M instance. Okay, last is the P struct. First, each P has a pointer to the M that it's attached to. So again, that relationship is bidirectional. Then it has a local run queue of G structs representing Go routines that are ready to be executed. When the current Go routine finishes, the runtime will check this local run queue first before it goes elsewhere to try to find executable Go routines. Then there's a run next slot. So if this has a G struct in it, then the Go routine associated with that G struct will be run next, instead of any of the Go routines in the run queue. And this property is used a lot with channel communication. So Goroutines that are sending and receiving can run back to back. And then there's a list of dead G structs, which are just empty Goroutine structs that can be reused by the runtime. So it doesn't have to allocate more every single time. And last up is the status, which can be idle if there's no Goroutine that needs to be executed right now. Running, which means the P is attached to an MG pair that is currently executing the Goroutine, or stopped for garbage collection. And that one is self-explanatory. So those are the main structs used by the runtime to track and execute Goroutines. But there is also a global struct and some global variables. First, the runtime has a global variable that is a list of all of the allocated G structs. And then it has similar global variables for M's and P's. And these are used for stuff like scanning during garbage collection and other runtime specific bookkeeping. Then there's the global schedule T struct. This has a global run queue of runnable Goroutines, which are separate from the local run queues on the P struct instances. And I'll go over which run queue the runtime will get Goroutines from in a bit. And last, it has a list of all the idle Ps and the idle Ms. So this struct mostly just holds some global state. These are the main players. Okay, so let's step through what actually happens in the runtime to solidify this model in your head. First, what happens when you create a Goroutine? So let's say we have a regular Goroutine that is currently executing. Next, our code hits a new Goroutine, where in your code you would say, go do this function. When you compile your code, any use of the go keyword is swapped out for a call to runtime.newProc. So when the code hits a new Goroutine, new proc gets called. And this function is defined in the proc.go file, and I'll leave a link to that source code in the description. Now, inside of the new proc function, Go will swap from the current user Goroutine into the system G0 Goroutine. So this process of switching to a new Goroutine is called a context switch and involves writing your current context into the sched property. And then the G0 Goroutine's context will be loaded from the sched property. So now, after we swap out the Goroutines, runtime code will be executing on the G0 Goroutine. And it will be used to spin up the new Goroutine we need. So the first thing we need is a G struct to represent the new Goroutine. And the runtime will either allocate or reuse one of the dead G structs from the dead lists. It'll first check the local gfree property for any of the unused G structs. Then it will check the global list of empty Gs on the sched T global struct. And if there aren't any reusable structs in those two lists, then a new G struct will be allocated with an included stack. Now that we have a G struct to work with, we need to set that up so that it is ready to execute. And this involves a bunch of different things. We need to clear any old state from the last Goroutine that this G struct was executing. We need to assign a new Goroutine ID to it. We need to allocate a stack if there isn't a stack and set the stack bounds, so the bottom and top address of the stack in memory. We need to populate the context so that when the Goroutine starts executing, it has a place to start from. And then the last thing is to add the go exit function address to the top of the stack so that when this Goroutine returns, the go exit function is called. And I'll go into more detail on that later. Okay, so the G struct is allocated, initialized, all ready to go. So next, its state is set to runnable, and it's added to the run next slot of the P instance that this G0, and our old Goroutine are associated with. And that's everything done to prep the new Go routine to be executed. So new proc returns, and we swap back from the G0 Go routine into our initial parent Go routine. And at this point, our state looks something like this, with the new gstruct stored in the P's run next slot. Any other runnable Go routines might be in the P's run queue, and our currently running Go routine in the m.curg property of your m. So this is what happens when you create a new Go routine. For the new Go routine to actually start executing, it needs to be picked up during a call to the schedule function. And there's a bunch of different paths that lead to the runtime calling the schedule function. So I will cover those next. Each path starts with an executing Go routine that either completes or is paused for some reason. Before we dive into this, I should note that these paths and flow diagrams are approximations, not necessarily perfect representations of everything that gets called by the runtime. So let's get to it. And the first case we'll cover is what happens when a Go routine completes. Like I mentioned earlier, after a Go routine function returns, the first thing that happens is Go exit is called, because again, that was added to the top of the stack before the Go routine was started. And inside the Go exit function, we again swap over to the system Go routine. So m.g0. So you can see that the G0 Go routine is where all the runtime specific code is all being run. While we're in the G0 Go routine, we're going to do a few things. First, any state specific to the completed Go routine is going to be cleaned up. Then we are setting the status of the gstruct to dead. And then we put the cleared and dead struct into a G free list so that it can be reused later. The pointers that the G and M struct hold to each other are also cleared. So after all of that, this is what our state looks like. We have a completed G that's disconnected from an M and a P struct that are still linked together. And the G0 Go routine is still executing. And the M now needs a new Go routine to run. So this is where we call schedule and where we'll find runnable Go routines to start executing. So internally, schedule will call find runnable, which will try to find a G struct with a runnable state that can be executed. And when it does this, it's going to search for a runnable G struct in a specific order. So first, if there's any runtime specific code, so like garbage collection or trace work that needs to happen, then that gets prioritized. And those are Go routines that the runtime handles. You don't need to worry about them. Then once every 61st call to the schedule function, Go will check the global run queue before looking at the local run queues. And it does this to avoid starvation of Go routines that may be stuck in the global queue waiting to run. Then it will check the local run next slot on the P that's running this G0 Go routine. Then it'll check the local run queue. And then if no runnable G has still been found, it will check the global run queue. Then it will check the network polar, which I will talk about in a bit. And then last, it will try to just steal some Go routines from the run queues attached to other P instances. So all of this boils down to two cases. First, if no runnable Go routine is found. And remember, we're still running on the G0 Go routine. So on that Go routine, we are just periodically looking for new runnable Gs. And if we don't find any, M will go to sleep after a while. And then the P is removed from the M. So the pointers are disassociated. And the P is put on an idle list. And in the sleep step, the runtime is actually parking the OS thread. The second case is if we find a runnable Go routine. So we do a few things. First, we change the state of the Go routine to running, indicating that it's being executed. Then we set the current G to the new Go routine that we want to execute. And we do the same thing on the G so that we associate them with those pointer properties. Then we switch back from G0 to the new Go routine, and the new Go routine starts executing. And that is how Go routines are picked up by the scheduler and run. Okay, like I said earlier, there are a number of different paths that can lead to the schedule function being called. The rest of them are cases where the Go routine is being paused for some reason. So let's look at those. The first case I want to cover is when a channel send or receive blocks a Go routine. So let's step through this. So we hit a blocking channel send or receive. The runtime needs to modify some state on the channel, so it needs to acquire a lock on that channel first. And then we will add the blocked Go routine to the channel's send queue or receive queue, depending on if it's a blocking send or a blocking receive. Then the runtime calls the go park function. And this is where we switch into our G0 Go routine again. So while we're running in G0, the paused Go routine's status is changed to G waiting. Then the G and M are disassociated. So again, we clear the pointers that connect them together. And now the M and P pair needs a new Go routine to run. So we go down and call schedule again. And then it goes through the exact same process we just covered. Okay, the next case is if we have a blocking network request. So first, while we're still in the user Go routine, Go will create a socket if there isn't an existing one that's already created. Then it will set the socket to non-blocking, which basically means that when you call something like connect or send on the socket, instead of blocking the OS thread until that operation is complete, it will return right away and tell you if the thread would have been blocked by that call. Then we register the socket with the network poller, which is kind of like a subsystem in Go's runtime, consisting of a bunch of functions. But basically what we're doing is registering a callback. So when the OS tells us that whatever call we made to the socket is done, we can wake up the Go routine and continue. And now is when the actual network request will happen. So we attempt to connect, read, or write to the socket. And if the OS says that that would have been a blocking call, meaning the socket is not ready yet, then we will add the current Go routine to the waiting slot for this socket. So when the network poller gets notified that the socket is done, it knows which Go routine to wake up because it is in the wait slot. And from here, we need to actually pause the Go routine so we can wait for the OS to complete the network request and notify the network poller. So it goes down into the same path as before, where we call the go park function, switch into the G0 Go routine, change the status of the G struct to waiting, detach the G struct and the M struct, and call schedule to get a new Go routine. So this flow in particular is really cool because the blocking network request would usually pause the OS thread, but because of Go's scheduling layer on top of that, we don't pause the OS thread, and then we're immediately able to run something else on top of the thread. Okay, the next flow that blocks a Go routine is a blocking system call. And this one works out very differently from the last two. So first we hit the code that we wrote that needs to make a system call. Then Go will call enter sys call block. And then in that function, we're changing the G's status to in a system call. We save the Go routine state in the sched property. And then we switch to the G0 Go routine. And this is where it gets more interesting. Instead of detaching the Goroutine's G struct from the M struct, we're going to detach the P from the M. And again, we do this by just clearing the pointer references that tie them together. And then we'll set the P's status to idle. So at this point, the G and the M structs are still associated with each other, and we have an extra P floating around, which tells the runtime that there is not enough work being done. So to fix that, if the runtime can find runnable work, so a Goroutine with a runnable state, then it'll try to run that Goroutine right away using the P that was detached. First, in the same G0 Goroutine, start M gets called, which tries to get a new M instance that we can run the Goroutine with. So we'll either pick up an idle M or create a new M. And when you create a new M, a literal new OS thread will be spawned. Then we associate the detached P and the new M together. So the OS thread starts up, and then it will call schedule to find a Goroutine to run. But if there isn't any Goroutine to run, then the P just gets put on the global idle list. We will swap back to our original Goroutine, and we execute the actual system call, which will block the thread. And then at some point, the system call will return and the OS thread will be unblocked. And again, even though the P is not attached anymore, the runtime still needs to do some scheduling work, like changing G back to runnable, so this Goroutine actually gets picked up again. So there's a number of times where a Goroutine is executing without a P attached, but it's mostly just for one-off runtime scheduling stuff. One other thing worth noting here is if the system call has the possibility to return quickly, then a different function is called than enter syscall block. And if the function call takes too long, then it will proceed down this same path. But if it returns fast enough, then the Goroutine can just continue on without all the scheduling overhead of queuing up all this other stuff. Go also has one more feature that will pause Goroutines if they've been running too long. It's called preemption, and it basically just prevents one Goroutine from hogging all of the computer's resources. This video's already gotten long enough though, so I decided not to do a whole preemption path here. So that is all I got for you today. If you want access to these diagrams, the link is in the description. And don't forget to subscribe if you want more videos explaining super confusing shit like this. And as always, keep breathing, keep building, and I'll see you next time. Peace out.